Welcome to Quantum Horizons, a podcast on the Decoding the Dark channel. If you like these kind of podcasts, don't forget to leave a like and comment down below a topic you would want a podcast about. Just a quick heads up before we begin. While our discussions are grounded in real mind-bending facts, this show is meant to spark your curiosity and is not intended to be used as formal scientific research. But for now, take a deep breath. Let the static of the day fade away. We've tuned into the deep dive, and today, we are pushing past the event horizon.
It's good to be back. And yeah, today's the day we stop looking at the map and actually start driving the car.
I really like that, because if you've been with us for the last 2 sessions of this deep dive, you know we've been hovering on the edge of the rabbit hole, right? We've been living entirely in the theoretical.
Very theoretical. Lots of abstract physics.
Right, like we talked about the spinning coin.
Yeah.
Superposition.
The idea that a bit isn't just a 0 or a 1, heads or tails, it's a ghost shimmering between both states.
Yeah.
Until you dare to look at.
Exactly. And we discussed those invisible cosmic threads of entanglement, that spooky action at a distance, as Einstein called it, where 2 particles separated by entire galaxies can still feel each other's heartbeat.
Which connects everything. It challenges our fundamental concept of space itself.
And of course, the environment, the fridge.
Yes.
Yeah.
The chandelier.
That delicate, dark chandelier, kept at absolute 0, colder than the void of deep space. We talked about how we have to build these massive golden cathedrals just to keep these fussy little qubits from collapsing the moment a stray microwave photon hits them. It's all very sci-fi, very mysterious.
It definitely captures the imagination, yeah.
It does, but I think a lot of you listening right now, maybe you're checking your emails, maybe you're stuck in traffic on the 405, and you're asking the one question that actually matters, which is...
why? The big so what question.
Exactly, why?
Yeah.
Why go through all this trouble? Why spend billions of dollars building these impossible machines that need to be kept colder than the universe itself? Is it just so we can, I don't know, download movies faster, play video games in 16K resolution?
Because if that's it, it's really not worth the headache.
Right.
And I can promise you, it is definitely not about checking email faster. I mean, if you used a quantum computer to check your email, it'd probably be the slowest, most expensive, and most frustrating email you ever read.
Okay, good. So we aren't just building a faster iPhone here.
Not even close. We are building a completely different kind of machine.
So that's our mission today. We are pivoting from the weirdness to the killer apps. We're looking at the problems that are literally impossible for classical computers, the ones we use every single day, but are child's play for quantum.
Right.
We're talking about simulating nature, revolutionizing medicine, and maybe, just maybe, saving the planet.
It's a massive agenda.
Yeah.
But it all starts with a fundamental realization about the universe we actually live in. And to understand that, we kind of have to go back in time. We need to go to 1981, to a conference room at MIT.
Set the scene for me. What's happening in 1981?
So picture the scene. It's the early 80s. The air is probably thick with cigarette smoke. It was academia in the 80s, after all.
Naturally.
And you have the world's leading computer scientists and physicists gathered together.
And what's the mood? Is everyone optimistic?
Oh, very optimistic. At the time, classical computers were getting better and better. Moore's law was really kicking in. Transistors were shrinking.
Right, the golden age of silicon.
Exactly. Everyone in that room thought, you know, if we just keep making these chips smaller and faster, eventually we can simulate anything. We can simulate the weather, the human brain, the entire universe.
And then Richard Feynman walks in.
The legend himself. He stands up, looks at this room full of optimists, and effectively throws a wrench into the entire machinery of computer science.
He dropped the mic before dropping the mic was even a thing.
He essentially said, "You're all wrong." His exact quote is famous for a reason. He said, Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical.
Nature isn't classical, damn it. I feel like I need that on a t-shirt.
It really is the bumper sticker for this entire field.
But what did he actually mean by that?
He meant something very specific. He meant that the world at its most fundamental level, the atoms, electrons, photons, it doesn't work like a classical computer. It doesn't work in binary. It doesn't work in rigid zeros and ones.
Because classical computers are logic machines, true or false, on or off.
Exactly. But nature is fuzzy. Particles exist as wave functions. They overlap, they interfere, they have probabilities, they exist in that state of superposition we talked about last time.
So when we try to simulate a molecule on a classical computer, like a laptop or even a supercomputer, we're essentially trying to force a square peg into a round hole.
It's worse than that. We're trying to force a multidimensional shimmering ghost into a rigid square box. And the problem isn't just that it's hard. The problem is the math. We call it the exponential explosion.
Okay, let's unpack this because exponential explosion sounds like a really bad day at a fireworks factory.
It does.
But I have a feeling you mean something specific about data.
I do. And this is the hardest part to grasp, because our human brains are just terrible at exponential numbers. We think linearly, 1, 2, 3, 4, but quantum mechanics scales exponentially, 2, 4, 8, 16, 32.
Okay, that I get. It doubles.
But let's see what that doubling actually does to a computer.
Yeah.
Let's take a simple example for the sources we looked at. Let's look at water, H2O.
2 hydrogens, 1 oxygen, the stuff of life.
Very simple molecule. A classical laptop can simulate the quantum interactions of a water molecule easily. It takes a few bits of memory, no problem at all.
Okay, so water's easy.
Now let's step it up. Let's look at the cup on your desk. Caffeine.
My personal fuel source.
Caffeine is C8H10N4O2. It has 24 atoms. Now, honestly, 24 atoms, that sounds tiny. It's completely microscopic.
Right, because my laptop renders 4K video games with millions of polygons, complex lighting effects, shadows, particle physics for explosions.
Right.
Surely, if it can render a literal war zone in Call of Duty, it can handle 24 atoms of coffee, right?
You would think so, but you're thinking in balls and sticks. You're picturing those plastic models from high school chemistry class? Static little balls connected by plastic rods.
Sure, that's how we all learn it.
But nature isn't static.
Mister.
In the quantum world, those atoms aren't in one place. Each electron in that caffeine molecule is in a superposition. It has a spin up, down, or both simultaneously. And here is the absolute killer. They are all entangled.
Meaning they talk to each other.
Meaning you can't describe one electron without describing all the others simultaneously. So let's do the math on that. If you have one particle with 2 states, that's 2 numbers to track. Easy.
Yep.
2 particles, 4 states. 3 particles, 8 states. 10 particles, 1,024 states.
It's doubling every single time.
Exactly, it's 2 to the power of n, and that doesn't sound too bad until you get to 24 atoms. By the time you account for all the electrons of those 24 atoms to describe the instantaneous quantum state of that one coffee molecule, just to hold that state in memory, you need about 10 to the 48th bits of memory.
10 to the 48th. That's a 1 with 48 zeros after it.
Correct. That is a massive number. Let's put that in human terms. Think of the Earth. Count every atom in the Earth.
Every atom.
The iron in the core, the sand in the deserts, the water in the oceans, the air in the atmosphere.
Okay, that's an unfathomable amount of atoms.
That is roughly 10 to the 50th atoms. So 10 to the 48th is about 1% to 10% of the entire planet.
Hold on, you are saying that to simulate one molecule of caffeine, just the stuff in my cup, I would need a hard drive the size of the planet Earth.
Essentially, yes. If you built a classical computer using every single atom in the crust of the Earth as a bit, it might just be able to hold the data for your morning espresso.
That is insanely inefficient.
It's the exponential explosion. And that's just caffeine. What happens if we try to simulate penicillin?
Which is bigger, but not that much bigger, right? It's just a mold.
Penicillin is C16H18N2O4S. It has 41 atoms at its ground state. So we go from 24 atoms to 41 atoms. Not a huge jump in physical size, but the complexity jumps from 10 to the 48th to 10 to the 86th bits.
And for context, how many atoms are in the observable universe?
Estimates vary, but usually it sits around 10 to the 80th or 10 to the 82nd.
Stop. Let me just pause there so you listening can let that sink in. To simulate a single molecule of penicillin perfectly on a classical computer, you would need more bits than there are atoms in the entire observable universe.
Precisely. It is physically impossible. You could turn every star, every planet, every speck of dust in the universe into a computer memory bit, and you still wouldn't have enough room to store the state of one penicillin molecule.
Wow.
This is what we call the classical wall.
That is deeply humbling. It really shows the limit of the machines we rely on so heavily. We think we're masters of the digital age, but we can't even model a simple drug.
It does, but this is exactly where Feynman's insight comes in. He said, don't use a classical machine to fake it. Build a machine that operates by the same exact laws as the molecule itself. Simulate nature with nature.
And that machine is the quantum computer.
Right, because a quantum computer uses qubits, which can be in superposition. It scales differently. To simulate that penicillin molecule, you don't need a universe-sized computer.
What do you need?
You need a processor with about 286 qubits.
From the entire universe down to 286 qubits.
Yes.
That is the efficiency gap we are talking about.
That is the raw power of speaking the language of nature. And this isn't just about abstract chemistry on a chalkboard. This has real-world, massive implications, which brings us to our first killer app.
Chemistry, and specifically the thing that powers our modern lives, batteries.
Right, we are moving from theoretical molecules to the messy, wet, highly chaotic world of lithium-ion batteries.
Because I feel like battery technology is the one thing that just hasn't kept up with everything else. My phone has more computing power than the Apollo missions, but the battery still dies by 4 p.m. Why is that?
It's a huge bottleneck. And the reason is that battery chemistry involves electrolytes, electrodes, and ions moving in incredibly complex ways.
Yeah.
Currently, R&D in batteries is very Edison style.
Edison style? You mean trial and error?
Exactly. It's like baking a cake. You mix some chemicals, bake it, meaning you build the physical battery prototype and test it to see if it works. If it catches fire, doesn't hold a charge, you throw it out and try a slightly different recipe. It takes months, sometimes years, to iterate.
And that's all because we can't simulate what's actually happening inside the battery at the molecular level.
We can approximate it, but we miss the crucial quantum details, specifically things like electrolyte complex formation. This is the stuff that causes capacity fade.
Which is why your phone battery is basically useless after 2 years.
Exactly. We really need to understand the reductive decomposition of ethylene carbonate.
Ethylene carbonate sounds tasty.
I wouldn't recommend drinking it, but simulating how that specific molecule breaks down over time is crucial. And this is where companies like Mercedes-Benz, Volkswagen, and IBM are teaming up. They aren't just waiting for the distant future. They're actively working on this right now.
Yeah, I saw that in the source notes. Mercedes and Sequantum, Volkswagen, and IQM, they are using something called the VQE algorithm.
Yes, the variational quantum eigensolver.
Okay, let's stop and explain that, because variational quantum eigensolver sounds like a weapon from a sci-fi movie. What does it actually do?
It's a brilliant piece of compromise, actually. We have to be completely honest with the listener here. The quantum computers we have today, they are noisy.
They make errors.
They make a lot of errors. They aren't perfect yet.
So how do you do precise molecular chemistry on a broken machine?
You use a buddy system. You pair the noisy quantum computer with a classical supercomputer. This partnership is what VQE is.
Walk me through that relationship. How do they work together?
Okay, imagine you are trying to tune a very complex guitar. You want to find the perfect pitch, which in chemistry is the ground state energy of the molecule. Because in chemistry, everything wants to be lazy.
Lazy.
Molecules want to relax into their lowest possible energy state. If you find that ground state, you understand the molecule.
Okay, so I'm tuning this guitar to find that lowest energy state.
The classical computer is the hand toning the tuning peg. It guesses a setting. It says, let's try this specific electron configuration.
It takes a shot in the dark.
It takes an educated guess, then it sends that guess to the quantum computer. The quantum computer, because it actually behaves like nature, can simulate that configuration instantly. It plays the note. It measures the energy.
So the classical computer guesses the shape, and the quantum computer calculates the energy of that specific shape.
Exactly. The quantum computer says, hey, this energy is high, it sounds sharp, and it sends that exact data back to the classical computer.
And the classical computer adjusts.
Right, it turns the peg down a little. How about now? It sends the new parameters back to the quantum processor.
It's a loop.
It's a constant feedback loop. Classical guesses, quantum checks. Classical adjusts, quantum checks. They do this thousands and thousands of times, spiraling down that energy landscape until they hit the absolute bottom, the ground state.
So we aren't waiting for a flawless million-qubit quantum computer to eventually replace our laptops. We are using the ones we have today as co-processors.
Exactly. And this VQE loop is exactly what Mercedes is using to simulate that electrolyte decomposition. They are trying to find the ground state of the chemicals inside your car battery so they don't degrade over thousands of charge cycles.
And if they find that ground state?
They find a battery chemistry that doesn't eat itself. They find a car battery that lasts 10 years instead of 2, or a battery with radically higher energy density, or, and this is a massive deal, a battery that doesn't rely on cobalt.
That's huge. Cobalt is a terrible ethical and supply chain nightmare.
It really is. If we can design it completely out of batteries using quantum simulation, that changes the whole EV industry overnight. It's the difference between blindly guessing the future and actually calculating it.
So that's energy. But let's move to something even more personal, our bodies.
Medicine.
Yes, this is perhaps the most emotive application we have. Drug discovery.
And this brings us back to another really classic analogy, the lock and key. This is a concept dating back to Emil Fischer in 1894. The idea is incredibly simple. An enzyme or a protein in your body is like a lock. A drug or a virus is like a key.
Makes sense.
For a chemical reaction to happen, or for a virus to successfully infect you, the key has to fit the lock perfectly.
Sounds straightforward enough. I have a key to my front door. It fits the lock. Done.
If only biology were that simple. The problem is, proteins aren't rigid metal locks. They are long, floppy chains of amino acids, and they fold.
They fold.
They fold into incredibly complex, tangled, three-dimensional shapes.
Yeah.
And they are constantly wiggling and vibrating.
So it's like trying to put a key into a lock that is literally made of jello and is constantly changing its shape.
That's a very good way to picture it. And predicting exactly how that protein will fold is one of the hardest problems in all of science. It's called the protein folding problem.
I've heard of this. It's tied to something called Levinthal's paradox, right?
Yes, Cyrus Leventhal pointed out that if a typical protein tried every possible configuration to find the right fold, just randomly trying different shapes, it would take longer than the age of the universe to finish folding.
There's that age of the universe metric again. Nature really loves to embarrass our human timelines.
It does. But here's the kicker. Nature does it in microseconds. Your body is folding proteins correctly right now, millions of times a second. Nature clearly knows a shortcut.
And quantum computers are trying to find that exact shortcut.
Exactly, because the folding process is fundamentally driven by quantum mechanics, by the minute interactions of electrons and charges along that entire chain. We have some incredible examples from the source material regarding this. Let's look at the SARS-CoV-2 virus.
The virus that causes COVID-19.
Yes, the viral envelope, the outer shell of the virus, is a model of about 305 million atoms. To simulate that viral envelope interacting with a human cell receptor is an exascale problem.
And this is where the collaboration between Moderna and IBM comes in. I found this part of the deep dive totally fascinating. Moderna, the company that gave us the mRNA vaccine, is actively looking at quantum.
They are, because mRNA is essentially an instruction set. It tells your body what proteins to build. But there are astronomically many ways to write those instructions. You need to find the specific sequence of mRNA that produces a stable protein that does exactly what you want, without side effects.
So it's another optimization problem.
It is. And they are using IBM's quantum computers, specifically the Heron processor, to run a version of that same VQE algorithm we just talked about. They are predicting stable structures for mRNA sequences.
And what are the results so far?
They are successfully predicting structures for 60 nucleotide sequences. Now, to be fair, that just matches what a classical supercomputer can do today.
So they haven't beaten classical yet?
Not on this specific task, no. But the difference is the trajectory. Classical computers are hitting a hard wall. Quantum computers are just warming up. As the qubit count goes up over the next few years, they will be able to simulate sequences that classical computers couldn't touch in a billion years.
That is the definition of future-proofing. But there was something else in the research that really caught my eye. It was a bit more, well, theoretical, a bit more fringe, but in the best possible way.
I know what you're talking about. You're looking at the quantum biorobot paper.
I am, and this blew my mind. The paper describes the interaction between the virus spike protein and the human ACE2 receptor, not just as biology, but as an actual quantum circuit.
It is a totally fascinating perspective. The authors propose treating the S1 subunit of the virus as a qubit.
A viral qubit.
Essentially, yes. And the binding process, where the virus actually latches onto your cell, is described as an entanglement event. They literally map it to a CNOT gate, which is a fundamental logic gate in quantum computing.
Wait, so getting infected with a virus is a quantum logic operation?
In this theoretical framework, yes, the virus entangles with the host. But here is the killer app part of that specific theory. If you view infection as a quantum circuit, you can design inhibitors, drugs, that act as a projective quantum measurement.
A measurement, like looking at the spinning coin and forcing it to be heads or tails.
Exactly. In quantum mechanics, when you measure a system, you freeze it. You collapse the wave function.
Right.
The idea here is to design covalent inhibitors that effectively observe the virus's wave function and collapse it into a state where it physically cannot bind to the cell.
That sounds like something straight out of Star Trek. Captain, we've collapsed the virus's wave function.
It really does, doesn't it?
But wait, explain the actual mechanism. How does a chemical drug measure a virus? Does it have tiny eyes?
No, no eyes. In quantum mechanics, a measurement is just an interaction that forces a choice. By designing a molecule that interacts with the virus in a very specific, targeted way, you force the virus's electrons to pick a state, and you make sure it's a state that doesn't fit the lock. You're using the fundamental laws of quantum mechanics to lock the virus out of your cells.
That is incredible. So we have batteries that don't die and drugs designed by collapsing wave functions. But let's zoom out.
Yeah.
Way out, we've been talking about atoms and molecules. Now let's talk about trucks.
Trucks, delivery routes, logistics, the macroscopic world.
This is the section on optimization, and it centers around a mathematical problem that sounds so simple but is actually a nightmare: the traveling salesman problem.
The TSP. It is the classic routing problem in computer science.
The scenario goes like this. A salesman has to visit a list of cities exactly once and then return home. What is the shortest possible route?
Sounds easy enough. If you have 5 cities, there are 120 possible routes. You can check them all on a napkin in a few minutes.
Okay, 5 cities is easy. What about 10?
10 cities gives you about 3.6 million routes. A modern classical computer can do that in a split second.
What about 20 cities?
Now you're in deep trouble. 20 cities gives you 2.43 quintillion routes. That would take a classical supercomputer centuries to solve perfectly.
And what if we go to, let's say, 61 cities?
61 cities. The number of possible routes is roughly equal to the number of atoms in the observable universe.
There's that comparison again. It really seems like the universe runs out of atoms very quickly when we start doing combinatorics.
It really does. This is called the factorial explosion. As you add just one more city to the map, the complexity doesn't go up by a little bit. It multiplies by the total number of cities.
And this isn't just about door-to-door salesmen, right? I mean, who cares about a salesman? This is about Amazon delivery trucks. This is about airlines. This is about drilling thousands of microscopic holes in silicone microchips. This is about pointing telescopes at stars.
It's about everything. It's about global supply chains, financial portfolios, air traffic control. Our entire modern economy is essentially a giant optimization problem that we are currently solving very, very inefficiently.
So how does the quantum computer solve a problem that has more answers than there are atoms in the universe? Does it just check them all one by one really fast?
No, that would take forever, even for a quantum computer. It uses a completely different approach. Uses an algorithm called QAOA.
The Quantum Approximate Optimization Algorithm.
Yes. And to understand how it works, it comes back to a landscape analogy.
I like landscapes. Paint the picture for me.
Imagine the landscape of all possible roads as a physical mountain range. Some roads are really long and expensive. These are high mountain peaks. Some roads are short and highly efficient. These are deep valleys. You want to find the absolute deepest valley.
Okay, I'm picturing it.
A classical computer is like a hiker who is blindfolded. It starts somewhere randomly on the mountain. It takes a step. If it goes down, it keeps walking in that direction. But it might easily get stuck in a small valley, or what we call a local minimum, and never find the huge, massive canyon right next door because it can't see over the ridge.
Right, it has to walk the path sequentially to know if it's good.
Yeah,
It's slow and it gets lost easily.
exactly. Now imagine the quantum computer. Because of the superposition, it doesn't have to be a single blindfolded hiker. It can behave like a fluid, like water. Imagine flooding that entire mountain range with water all at once. The water naturally flows down. It fills the valleys instantly. It doesn't have to painstakingly climb the mountains. It just naturally settles into the lowest possible points.
And there's tunneling too, right?
Yes, quantum tunnel. If there is a barrier, a mountain ridge, between a good solution and a great solution, the quantum water doesn't have to go over it. It can tunnel right through the mountain. It flows through the complex landscape, naturally settling into the best or near best solution.
That is a beautiful image. It tunnels through the bad answers to find the good one.
It finds the optimal solution in a fraction of the time. If we can crack this with stable qubits, we aren't just saving time, we're saving billions of gallons of fuel. We're saving energy, saving money. It makes the entire global infrastructure vastly more efficient.
Which is a perfect segue to our final killer app. We've talked about saving battery life, saving human lives with drugs, and saving money with logistics. Now let's talk about saving the actual planet.
Climate change, the ultimate optimization problem.
The sources for this deep dive highlighted three main areas here. And the first one really, really surprised me. Fertilizer.
Nitrogen fixation.
Yeah.
It's arguably one of the most important chemical reactions on Earth. We need ammonia to make fertilizer to feed the global population.
And right now, we do that with something called the Haber-Bosch process.
Yes, invented in the early 20th century.
Yeah.
It takes nitrogen from the air and forces it to bond with hydrogen. But nitrogen is incredibly stubborn. It has a triple bond. It holds on to itself very tightly.
So we have to force it.
We use immense heat, like 500 degrees Celsius, and immense physical pressure. It is a violent, brute force industrial process. Giant factories burning natural gas just to break those microscopic bonds.
I read that this single process consumes something like 1 to 2% of the entire world's energy supply.
It does. It is a huge carbon emitter. But here's the irony of it all. Nature does this for free, at room temperature, right in the soil beneath our feet.
Bacteria.
Bacteria use an enzyme called nitrogenase. It gently grabs nitrogen and snaps it together with hydrogen effortlessly. No high heat, no massive pressure, just elegant, quiet chemistry.
So why don't we just copy the bacteria? Why are we building these massive polluting factories?
We've tried, but we cannot simulate nitrogenase. It contains a specific cluster of iron and molybdenum, the Fe-MoCo cluster, that is incredibly complex quantum mechanically.
The classical wall again.
Exactly. The electrons in that cluster are strongly correlated, meaning they're all entangled in a complex dance. Classical computers just choke on the math. We literally don't understand how the enzyme works, because we can't model the electron interactions.
But a quantum computer?
Quantum computer could model the Fe-MoCo cluster perfectly. If we can understand the mechanism, we could design artificial catalysts that do exactly what the bacteria do. We could manufacture fertilizer at room temperature.
That would slash global energy consumption overnight. That is massively impactful.
It is, and that's just one example. The second one is solar capture.
This involves perovskites, right?
Yes. Right now, most solar panels are made of silicon. They are great, they're cheap, but they max out at around 20 to 25% efficiency. Perovskites are a different crystal structure that could theoretically reach 35% efficiency.
It's almost double. That changes the math of solar power completely.
It does, but perovskites are fussy. They are hard to stabilize, they degrade quickly in moisture, and some of the best ones contain lead, which is obviously toxic.
So we have a super material, but it falls apart and might poison us.
Exactly. We need to find the perfect combination of materials to dope the crystal, to swap out specific atoms to make it stable, efficient, and safe. That is a massive combinatorial problem. Billions of possibilities.
Enter the quantum computer.
Enter the quantum computer.
Yeah.
Simulating those doping combinations simultaneously to find the Goldilocks material. If we can get solar panels to 40% efficiency and make them cheap and stable, the economics of global energy change completely. Fossil fuels couldn't compete.
And the third climate application, carbon capture.
Direct air capture, pulling CO2 straight out of the sky. To do this efficiently, we need novel solvents, liquids or materials that bind tightly to CO2 but nothing else, and then release it easily when we want to store it. Designing those molecules is, again, a pure quantum chemistry problem.
It really feels like all roads lead back to molecular simulation, whether it's batteries, life-saving drugs, fertilizer, or carbon capture. It's all about understanding exactly how atoms dance with each other.
That's the core thesis of this whole field. Feynman was right. Nature is quantum. If we want to fix the huge problems we've created in nature, we need tools that speak the same language.
It's a really powerful idea. We aren't just building faster calculators here, we are building a translator for the universe.
That's a lovely way to put it.
So we've covered a lot of ground today. We've gone from the impossibility of simulating a mold spore to the logistics of global shipping networks.
We definitely have.
What's the ultimate takeaway for you? When you look at all these killer apps, what's the thread that really connects them all?
For me, it's the shift from discovery by accident to discovery by design.
Tell me more about that.
Well, for all of human history, chemistry and material science have been largely trial and error. We find a plant, we eat it, we see if it cures a headache or kills us. We mix random metals in a forge, we hit them with a hammer to see if they are strong.
The Edison approach.
The Edison approach. And to be fair, it has served us very well. It got us to the moon. But we are reaching the hard limits of what trial and error can do.
Yeah.
We are facing global-scale problems like climate change, incurable diseases, energy crises, where we just don't have the time or resources for a million failed physical experiments. Quantum computing offers us a way to simulate those million experiments in the digital realm using the actual fundamental laws of physics and find the correct answer on the first try. It is a shortcut through complexity.
That's the so what. It's not about speed in the sense of a faster video game or a quicker web browser. It's about the speed of human innovation.
Precisely. It accelerates our ability to invent.
I want to leave you listening with one final thought, something to just chew on while you drive home or finish up your workout. We talked about that paper on the virus earlier. The idea that biological processes, protein folding, viral binding, can be accurately described as quantum circuits. That nature is, in effect, performing quantum computations every single second.
It's a very compelling hypothesis.
So if a virus is essentially a primitive quantum circuit, and our cells are performing quantum measurements just to function, does that mean we are just biological quantum computers walking around?
That is a very dangerous question to ask a physicist. But honestly, if you look at the sheer complexity of the human brain, the unbelievable efficiency of our biology, it is certainly possible that we are leveraging quantum mechanics in ways we don't even begin to understand yet. We might be building these massive freezing machines just to figure out how we ourselves work.
We are building the mirror to see our own quantum reflection.
Perhaps we are.
Deep stuff. Well, if you found some peace in the quantum shadows today, or if you're just really excited about a phone battery that lasts a week, leave a like and support the show. This is the Decoding the Dark channel. We hope to see you again.
Keep wondering.
Until next time, keep your superposition stable. We'll see you in the next deep dive.